Hi, this is Tom Cecil, and I'm here today to give a talk about AI-driven EDA for the eBeam Initiative's Fine Line Video Journal. So I'll start off this talk by talking about a presentation I made at SPIE in 2020 talking about establishing fast, practical, full-chip ILT flows using machine learning. And in that talk, I referenced an Economist article from a few years before talking about data replacing oil as the world's most valuable resource. And it listed off some tech companies who definitely are harvesting data from every avenue that they can. And in that talk, I talked mainly about supervised machine learning, talking about us having the luxury of being able to create a lot of synthetic, programmatic data rather than to rely on humans to generate that data like some of these other companies need to do. And we argued that we could use ILT to create very high quality mass synthesis data to train machine learning models, and then we wanted to build some supervised deep neural nets to replace the ILT process with a machine learning model. And so that has been successful, and in the rest of the talk today I'm going to talk about other areas where we can now extend deep learning or artificial intelligence beyond just the supervised learning space. So first thing I'll continue to comment though is on how supervised learning has made its way into a lot of the other parts of mass synthesis. Modeling, definitely, in terms of some advanced resist, etch, mass 3D, and other places. There's a lot of areas where machine learning modeling can help us get either some extra accuracy or better runtime versus conventionally modeled techniques. Assist features, this is very similar to the machine learning ILT technique. Similarly for OPC, there's multiple ways that we can use the machine learning models in different forms of machine learning networks to help give better solutions there. And also in hotspot detection, which is a little bit different in that it's not being used to create a mask or create a model, but it's actually being used to identify things that otherwise, maybe perhaps using a rigorous solver, might be too slow or too difficult to analyze in detail, and it can give suggestions about where to look for problems and things like that. So it's really an aid to help the whole mass synthesis flow work in a better way. So the first of the areas I'm going to talk about, I'm going to talk about three areas: optimization, data analysis, and generative AI. And the first one is going to be talking about how can we use optimization across the full stack, and how is it being used, and how can we kind of migrate some of the ideas or techniques from other areas of design where it's being exploited into this manufacturing and mass synthesis space. So within Synopsys, we have a number of areas across the full stack where we've used optimization in better ways to help improve upon the best-in-class solutions that we would currently have, where humans would have had to make some decisions, or maybe heuristics would have to be used, or maybe machines tried to do something, but they just weren't as good as using some artificial intelligence to boost the solution. So we could ask, where is this kind of optimization useful within the mass synthesis domain? You might say, well, it's probably useful everywhere. We can optimize anything. But really the areas that I'm going to focus on are places where human setup and heuristics kind of guide us, or maybe even limit, let's say, the best in-class solutions. And those are the areas that we would like to target. This is a little bit different than the supervised machine learning I talked about before. We would say, well, we're just kind of replicating what some software can do, maybe in an iterative fashion with a deep network. Now we're talking about what is something where a human has tried to work on something and put their intelligence into something, or their hard work, and can some kind of artificial intelligence mimic that and give us a better solution. So if we look at the space on the right side in this figure, there's some things we can use to guide us towards things in the manufacturing space. For example, test pattern creation from one node to the next node, or from one node modeling patterns to the next modeling patterns, or even what are the best modeling patterns to actually analyze and collect. In model calibration, you could ask the question, are some initial conditions that you use to set up your model calibration actually determining the quality of the model? And if so, those initial conditions might have been chosen by a human, and maybe some artificial intelligence engine could choose those in a better way to actually allow you to get to a better solution for your model. I think in the design space optimization, this is a technique which has been very successful, that kind of idea. There's also complex trade-offs, for example, quality of results, runtime, model size, model memory footprint. These kind of things are sometimes very difficult for humans to understand how to trade off in a judicious way to get to some best-in-class solution, because maybe our understanding of the relationships between those things are not as refined as a machine learning model would be able to understand. Similarly, in the mass synthesis space, there's trade-offs between lithographic quality, runtime, mass complexity, and these things are often very difficult for humans to be able to really understand how to trade those things off against each other, but the machine can learn those things. Okay, next area is talking about data and data analysis, and the question could be, what other data is available that we have access to, but it's not really being harvested? Maybe it's being thrown away, or we're not analyzing it fully. In Synopsys, we have a couple different tools that actually are really trying to exploit this data outside of the mass synthesis domain. The first one is called fab.da. This one is trying to get information from any tool that they can get it from within the fab and gather that, analyze it, and give you a much better idea of how to do yield management, root cause analysis, and this type of thing, so that you can make much better decisions faster and get early insights into what's going on with your processes. The second one is called silicon.da, and this actually is driven by putting some in-chip monitors into the silicon that can be monitored and get feedback in many stages of the design ramp up, in design, ramp, and in production. It gives feedback for what's going on in the silicon, and basically what we call the silicon lifecycle management is being able to tell us, how to maybe give information upstream back to the designer, even to how to tune things to actually get better performance and maybe not be as restrictive as if some just rules were used. So both of these areas can give us ideas that we can bring back to the manufacturing and mass synthesis space. And that's what I'll talk about on this page. So ideas from FabDA. Where's there data that we can get a lot of, but maybe we don't use all of it? Maybe we only use a tiny bit of it. Maybe in our OPC and ILT solution, we run many iterations, and maybe all those iterations have some data maybe early in the process, but we are not actually using all of that information. And maybe we're only using the final mask. Also for LRC, maybe we're only getting a summary report, similarly for mask inspection, just getting a summary report of what failed on the chip. And maybe there's actually a lot more data there that's not being used that we could actually try to analyze and have a AI model try to understand, to give us more feedback about other things that maybe aren't at the beyond the spec of failure, but something else that can make this solution healthier. Also, model calibration data. There's probably a lot of data that's gathered in the model calibration plates that maybe is things that are not going to be used and selected to calibrate the model, but still could be used to give other information that could be valuable. In the silicon DA ideas, could we think about, for the in-chip monitor, what's a generalization or analog of that in our space? Maybe there's something in the chip as the mass synthesis recipes or solutions are being developed that can give feedback or be monitored to help you tune parameters as things are going on. Maybe you would say, well, I'm going to tune some parameters and just look at the LRC failures and see which one is better. But maybe there's actually more detailed result beyond just the LRC that could be fed back to help you tune the parameters in a better way, or some automatically AI type solution could try to learn how to tune those parameters based on either LRC or other metrics that maybe we don't completely understand exactly how to map them to something in the LRC, but they're still lithographic metrics which are quantifying something. And maybe the combination of those things, as I say in this last one, some combination of lithography characteristics perhaps are predicting failure better than a human would say, well, I know I have a need to get a certain ILS or a certain EPE or a certain MEF, and all of those things together will meet certain specs, and that will mean I'll get a certain yield. But maybe it's something much more subtle and some very nonlinear combination of those lithography things, or maybe lithography metrics that we're not even aware of measuring, that AI could understand and use to help us say, this is actually how to better predict when failure is going to happen. Okay, the third area after optimization and data is the Gen AI. And the question I say we could pose is, where are we actually creating something that's similar to what's been created previously? And this picture here shows a kind of hierarchy of solutions which could be helpful in the EDA area using Gen AI. And the x-axis is showing some kind of investment and maturity to bring something to production, and the y-axis here is showing the productivity and time to best results impact that these things are having. And we can start at the bottom are things like, okay, can we learn about queries people have had or questions they've had about how does the tool work or how to use it best, or things like that, like Stack Overflow, things like that. Maybe this thing can be quantified in some certain way to help the user work in a collaborative way. And maybe some simple scripting can be done, and the user will collaborate with the AI to get a better solution. Then there's a little bit higher level, which is more, you say, like generative, where here maybe the inputs have to be a little bit more complex, but then the outputs could also be more complex and more capable than in the collaborative methodology. And at the top, which is the most valuable, would be some kind of automatic EDA agent, which could even take something as straightforward as natural language, allowing a much wider set of users to potentially build prompts to help drive a tool which could then automatically do some design or verification in an autonomous way. So the question will be is, how can we take some ideas here kind of focused on design terminologies and domain back into the mass synthesis space? So the question I kind of think about when I think about these foundational or GPT models are, maybe there's something in the latent space within the deep learning model that's hard for us to access programmatically, but the large language or pre-trained transformer models can understand. Because if we could access it programmatically, we could just write a program to say, oh, here's your natural language input, here's the design output. But it's just something that we're not able to get to that kernel of truth or the program to be able to actually do that. But somehow inside of these giant models, they're able to understand how to actually programmatically in some way achieve that goal. So some areas where we could say, what are things that are created that are similar to previous iterations or versions that we would want to say, we could hope there's a foundational model that could comprehend what it's seen before and build upon it to make some kind of extrapolation towards what you might ask it to do in the future. Lithography models and parameters. There's a lot of source shapes that have been tried in the past, and a lot of resist parameters and other things that have been tried in the past. And probably, there could be some foundational model which could encompass all of those parameters and be able to build a model in, in a simpler way with a simpler type of input description. Perhaps ILT, OPC, and ILT recipes and scripts to figure out, I need to do this type of optimization, and I need to have these kind of metrics and a lot of things. Maybe some of those things could be generated in some way, in some of this sort of generative or collaborative way, in an easier way. Obviously, you could say the supervised learning that I talked about at the very beginning, talking about taking trained or ILT mask and training a machine learning model and saying that's a supervised thing. Maybe that could be even more generalized to say we can build some foundational model of ILT that would take in a different type of input. Doesn't need to just take in a design, but could take in something even simpler, and it doesn't need to actually be trained. It's already been trained on enough data that it could just produce a solution for you, just taking as design as input or something like that. And also debugging. Definitely there's debugging that's done on by thousands of engineers around the world, and they're doing probably many of the same things over and over again, even that they themselves have done before. And this seems definitely an area where this methodology probably could be captured because it's something that's been repeated so much. So in summary, I've talked about 3 different areas: optimization, data analytics, and generative AI. And I've tried to talk about some areas within Synopsys where these are being used across a stack of the design to manufacturing space, and how we can think about in the mass synthesis space, we could use some of those ideas and actually get a lot of benefits within mass synthesis. And so that's the end of the talk, and thank you for attending, and I'll see you next time.